Hello friends, welcome to the online lecture series of St. Andrews Institute of Technology and Management, Gurugram. Myself Satinder was Assistant Professor in Etce department. So our topic in today's lecture is Algorithmic State Machines and Binary Adder using FSM. We will see in the lecture how we can implement a binary adder or can design a binary adder using the FSM. We can use Mealy model or Moore model, and then we see the algorithmic state machines. So it is a part of digital electronics in unit 4th. Okay. So here let's start with the binary adder. We have already seen the FSM's finite state machines in the last lecture, where we saw the Mealy model and the Moore model of finite state machines, and we have implemented a logic circuit using flip-flop of a sequence detector using Mealy model. So in this lecture we will see how we can implement a binary adder. That is, binary adder is a adder, you all know, that is used to add two binary bits, that is 0 0 or 0 1 or 1 1. So here let's start. Here we, in a binary adder, we can have inputs 0 0, so sum would be 0. If it is 0 1, the sum would be 1, or if it is 1 0, the output would be 1. And the last one is, if both the bits are 1 1, the output, that is the addition, would give us some 0 and a carry. This is the important part. The carry would be generated and it would be 1. So if the inputs are 0 0, the sum would be 0. If inputs are 0 1, the sum would be 1. But in case if both the inputs are 1, the output would be 0 with a carry 1. So we will implement it using a Mealy model of FSM, finite state machine Mealy model. So let's say we have two states to implement it, state 1 S0 and state 2 S1, in which state S0, the circuit would be in state S0 if the sum is 0 or 1 without any carry generated. System would be in state S0 if there is no carry generated, or it will move to state S1 when carry is generated. That is the fourth case, in which both the inputs are 1 1. So we divide our system in two states, S0 and S1. Okay. So now let's see how we can implement. We have two inputs here, two states, that is S0 and S1, and since we have two bits to add, we have two inputs, that is 0 0 or 0 or 1 1 0 or 1 1. So we have two input bits. That is why I have shown here two input bits in the input, and output is a single bit. Okay. So let's start. If it is in the initial states S0 and we get the input 0 0, so output would be 0 and it would remain in the initial state, as there is no carry generated in this combination. For this combination, okay, it will remain in state S0 for this combination as well, in which 0 and 1, the sum would be 1, and for this combination as well, 1 0 and the output is 1. So for all these three combinations, our adder will remain in state S0 as the carry is not generated. Now let's move to the fourth case, in which the inputs are 1 1. So output would be 0 and our system would move to state as 1. Output would be 0 as 1 1 will add to produce a 0 and carry is generated. So our system has moved to state as 1. Okay. Now if it is in state 1, what are the possible transition case over there? Let's see. If it is in state 1 and the input bits are as it is in state 1, since the sum is 0 and if I add it with 0 1, okay, the input is 0 1 and a carry was also there, so when I add them it will give 0, but a carry is generated once again, so it will remain in state 1 for this combination. Okay. Or if I get 0 1 as we have over there, 0 1 and a carry 1, so it will again generate sum 0 and carry 1, so it will remain in state 1 again for this combination. Now when will it move to state initial state, that is the in the case when carry is not generated. So let's see, it will move to initial state only when we get a 0 0, that is 0 0. So output will be 1 0 0, that is 1, and carry would be 0. So in this case, in this particular case, input is 0 0, so output would be 1 as I have shown on the transition line, and it will move to the state S0 again as there is no carry generated. So this is how we can design a binary adder using a simple finite state machine. Okay, we can also draw it using more machine, so you can try it to implement a binary adder using a more model of FSM. So now let's move to the next topic, which is the algorithmic state machines. So what is an algorithmic state machine? It is again also a method for designing a finite state machine. So we will see again how we can design finite state machine using an algorithmic state machine. It is also used to represent diagrams of digital integrated circuits. Okay, we will use it to design the diagrams of digital integrated circuit. The ASM diagram is more structured and easier than the FSMs. So we will see how we will design an FSM chart from the state diagram of a FSM. So ASM chart is a method of describing the sequential operation of a digital system. Sequential operation of a digital system or a sequential circuit. Okay. So ASM method composed of the following, some of the following steps. Like first is first of all we would create an algorithmic to describe the operation of the device, desired operation of the system. We will create an algorithmic using a pseudocode. We will use a code which is not in our syllabus. Our syllabus consists only the ASM charts. So but we should know what is an ASM. So we will first for an ASM, we will create first the algorithmic to describe the operation of the device. Second, convert this code of algorithm into an ASM chart. So in second step, we will convert the algorithm which we have already created using a code into an ASM chart. In third case, we will design a data path based on this ASM chart, and finally the control logic. So first we will create algorithm, then ASM chart, then the data path, and in last we will design the control logic. But this is all is not our in the part of our syllabus. I have just summarized some points how we can design an ASM. Okay, so what is in our syllabus is ASM chart. So let's see what is an ASM chart. An ASM chart consists of interconnection of 4 types of elements. So it is nothing but a chart which consists of 4 elements, that is state name, as we will convert an FSM into ASM. So FSM consists of some states. Any system would be in a state for particular instant of time. So we will have state name, then we will have state box, we will have decision box, that is conditional box or decision box, and conditional outputs. The conditional outputs would be used only in case of melee machines. In more machines, conditional outputs are not condition box are not used in conditional output, or conditional box are used only in the melee machine. In more machine they are not used. Okay, so we have three boxes: state box, condition box, that is decision box, or conditional output box. So state box is a rectangular box, decision box is a box, diamond shaped box, and condition box is an oval shape box. Okay, so condition box is a diamond shaped box or decision box, state box is rectangular, and conditional box is oval shaped. So here we have an example of a melee state diagram which we will convert into ASM chart. So let's see how can we convert it into an ASM chart. Here we have with us an state diagram of a melee machine. Here we have 3 state: S0, S1 and S2. So the system moves to S1 if the input is 1 and output is high. Okay, then S1 moves to S2 if input is 1 and output is 0. Similarly, it moves to state S0 from S2 if input is 1 and output is 1. It remains in state S0 if its input is 0, output is 0. Remains in state 1 if input is 0, and remains in state 2 input is 0 but output is also 0 in this. So this is a diagram which we will try to convert in an ASM chart. So let's see. So here I have drawn it again so that it will be easy for us to convert it into. I have drawn it here again, the melee state diagram. So as we can see, the first state is S0. So this is the state box and this is the input X we are providing. So if input is 0, so this is the decision box, that is if X is 0, the system remains is in S0. Okay, if X is 1, then the system moves to state S1. As I have already told you that there will be a conditional output box as well for melee machine. So it will move to state 1 through this condition box where Z is conditional output box where z is the output. Okay, so when input is 1, output is high, so it will be z is equal to 1 in this case. Okay, I have not shown in this figure, but z would be 1 when it transit from 0 S0 to S1. Similarly, we can see in the state diagram when it is in state 1, and if the output if the input is 0, it will remain in, if input is 0, it will remain in state S1, but the output is high. I have forgot to tell you that this box will be used only when the output z is high. If output z is 0, we will not use this conditional output box. That is why I have not denoted z is equal to 1, because it is self-implied that z will be 1. That is why we have shown this. Okay, if it is high, only then we will show this conditional box. So as in this part, input is 0 at state 1, input is 0 and output is 1, so we will be in state S0 but output is high. If like this, if input is 1, it will move to state S2 and the output is 0, so we don't need a output box over there. Okay, now if it is in state 2, if it is in state 2, if it is in state 2 and input is 1, input is 1, so we can see output is 1 also. So we will use a box, condition output box, and it will transit to state S0. Okay, and if x is 0, then it will remain in S2. So this is how we can make our ASM chart using the Mealy state diagram. Now let's see one more example for a more state machine. How can we draw an ASM chart for a more state machine? We are given with a state diagram of the machine in this example. Here we have a state diagram for the more machine, as we have already know that the output would be in the circle with state. The output is in the circle with state, and the transition line only consists of the input values given to the system. This is the fundamental of more systems, in which output is in the circle with state. So in this case also, let's see how many states we have. 3 states. Okay, we have 3 states, A, C and B, and we have, it is a more typical one, we have 2-bit input, that is x, y, 0 0 0 1 1 0. So I have denoted it here 1 1 or 1 1 0 1 1 0. Okay, so input is a 2-bit number, x and y, 2-bit stream. Input is x, y. In the last example we have only 1 bit. Okay, here we have 2 bits. So let's see, it is in state A, first state A, and as the output is also to be denoted in the circle, we have denoted output in the state box itself, z is equal to 1. In state A, z is equal to 1, and if now input is given, that is x, y is given, so how many combinations of x, y can be there? 0 0 0 1 1 0 1 1. Let's say if x is 0, if x is 0, then we will have 2 possibilities of y, that is 0 and 1, and if x is 1, then we have 2 possibilities of y, that is 0 and 1 as well. So 4 combinations are there for x and y. If x is 0, in this case, let's see, if x is 0, that is this one, x is 0, okay, in this case x is 0 and y is 0. So for x 0 and y 0, it will remain in the state A. And if x is 0 and y is 1, if that is this case, if x is 0, y is 1, it will move to state, which state? This one, it will move to state B in this case. If you can see from the transition state machine diagram that if x is 0 and y is 1, it will move to the box B. Similarly, if x is 1 and y is 0, then it will move to state B. Otherwise, if x is 1 and y is also 1, if x is 1 and y is also 1, so it will move directly from A to state C, as you can see in the state diagram. Now if it is in state B, okay, so here also we have 4 combinations. For x is equal to 0, y can be 0 1, and for x is equal to 1, y can be 0 1 0 1, okay. So using the state diagram table, we can again make the ASM chart using if x is equal to 0 and y is equal to 0, it will remain in state B, and if x is 1 and y is also 1, so it will move to state A, as we can see over there. If both the inputs are 1 1, then it will move to state A, so we have moved to state A, okay. If inputs are 0 0, it will remain in state B. Similarly, in state C, if it is in state C, for 1 1 inputs, it will move to state B, or for 0 0, it will remain in state C, okay. This is how we can generate the ASM chart from an FSM, finite state machine, whether it will be milli or more. We can convert both of them into an ASM chart, okay. So this is it for the lecture. In this lecture we have learnt about the ASM chart and the binary adder using FSM. Thank you friends.